Hi everyone, welcome back. In this video, we're going to look at the force that a wire would feel if it was placed in a magnetic field and had a current passing through it. Okay, so just like charges experience a force if they are moving perpendicular through a magnetic field, well, just think about what a current is. A current is just a steady stream of charges moving through a conductor. Okay, so each of the charges are going to experience a force if they're put into a magnetic field, and so the wire as a whole will experience a force because of all the charges inside it experiencing that force. Okay, so we're going to look at that. Here's the equation straight off the bat. So you've got F equals NBIL. So F is the force on the wire, N is the number of wires possibly bundled together. Okay, this is especially true when we look at motors later on, where motors are typically built by coiling a wire around multiple times. Okay, so we'll look at that later on. B is the magnetic field strength, I is the current in the wire, and L is the length of the wire contained in the magnetic field. Okay, that's really all it is. Okay, so F equals NBIL. Just make a note that your wire has to be perpendicular to the field. If it's parallel to the field, just like with moving charges, they're not going to experience a force. Okay, so they have to be perpendicular. Okay, so like I said, electric current can be considered a stream of positively charged particles. Okay, this is conventional current we're talking about. In reality, it's the electrons that are moving, but to make things simpler for us in physics, we just consider it to be positive charges moving the other way, and then we call that conventional current. Okay, so again, if you've got this stream of charges passing through the field at a right angle, then each of the charges will experience a force. So the stream as a whole will experience a force. Okay, and if your current contains these moving particles, then your wire will experience a force. Okay, so that's all we're talking about here. Okay, just multiple charges at the same time experiencing that force. So where does this equation come from? Okay, now this you technically don't have to know, so you can skip to the end where we do a question, but I think it's nice to know. And this is just a very sort of hand-wavy derivation of this equation. So if we talk about the current in a wire, current is, or can be defined as the rate at which charges pass through that wire. Okay, so if you want to give it an equation, you can write it as current equals Q divided by T, where Q is the amount of charge moving past a particular point in a certain amount of time T. Okay, we can rearrange this, put it as Q equals IT, and we'll leave it at that. Okay, that'll become apparent in a second. Okay, at the same time, if you've got charges moving through a wire and the wire has a length of L, then if the time it takes for them to move that distance, L, is T, then we can write the velocity of these charges as length divided by T, okay, distance over time. That's just your speed equals distance over time formula. Okay, so we can write the velocity of these charges moving through the wire as L over T. Okay, where L is the length of the wire, T is the time it takes for them to travel that length. Okay, so we've got this phrase up here for Q, we've got this phrase here for V. You might be able to see where this is going. Okay, what we're going to do is we're going to put these expressions for Q and V in the equation F equals QVB. Okay, so replacing Q with IT, that's done here. Replacing V with L over T, that's done here. You notice that the T from the IT will cancel with this T in this fraction, so they're gone, leaving you with I times L times B, and that's where that part comes from. So F equals BIL. Okay, where's the N though? We don't have the N. Well, if you just bundle a bunch of wires together, then each wire will experience the same force. So if I've got 3 wires, they'll be experiencing 3 times the force. If I've got 10 wires, they'll be experiencing 10 times the force. So that's where the N comes from. Okay, it's not really derivation of any kind, you're just multiplying the number of wires that you have. All right. And again, the direction of the force is determined by using the slap rule. Okay, so we've got moving charges, they're moving through a field. You want to work out which direction the force is, slap rule. Okay, and most of the time we're talking about conventional current, so you're going to be using your right hand. Okay, so just remember the fingers are the magnetic field and the thumb is the direction of the current in this case. And your palm is going to tell you which direction that force is going to be. All right. And one more time, I'll just say it again because people are going to forget. The force only applies if you have the current, or at least a component of the current, that is perpendicular to the magnetic field. If the current is parallel to the field, no force. Okay, just like when charges move parallel to a field, no force. All right, so let's do a question. So it says, determine the magnitude of the force applied on a single power line cable, which carries a current of 100 amps, assuming the magnetic field strength of the Earth is 5 times 10 to the negative 5 Tesla. The length of the cable in the magnetic field is 20 meters. And I guess we're assuming here that the current and the field are perpendicular to each other. Otherwise, what's the point? All right, so let's draw a picture just so we can sort of visualize what's going on. So here's your power line cable. Like, let's say the current is going that way. Let's draw some field lines. There we go, so that's our field. It could possibly be this setup. It doesn't tell us the directions, so we just have to make them up ourselves. All right, and our job is to work out the magnitude of the force that this cable will experience. Okay, so that's just using F equals NBIL, because we're talking about a current rather than a single charged particle. N is the number of wires. It tells us there's only one wire, so that's just 1. B is the magnetic field strength, which is 5 times 10 to the negative 5. I is the current through the wire, which is 100. And the length of the cable in meters is 20. Okay, if we put all that together, let's work it out. I haven't done the working out beforehand, so hopefully it all goes good. 1 times 5 times 10 to the negative 5 times 100 times 20, 0.1. There we go. All right, that's it. Okay, that's all it is. Okay, if your current is perpendicular to a magnetic field, you can use F equals NBIL to work out the force that it would experience. And if you wanted to, you can use your slap rule to determine the direction of that force. So in this case, the way that I've drawn the picture, the force will be, well, let's do it ourselves. So make your fingers point in the direction of the field, which is to the right. Make your thumb point in the direction of the current, which is up. Okay, so if you're doing that right now, your palm should be facing away from you. Okay, which according to the picture, that means the force will be into the page. So we can describe that force with an X. And there you go. Force is into the page. Okay, that's all it is. So we'll stop there, and I'll see you next time.